to it. Okay, so I have a little note for myself. I was charging my pencil. So we will start. We're continuing with chapter 2. We will start where we left off. So I left myself a little note so I can know exactly where to start. We're talking about the behavior of the electron, which is the same thing as the behavior of the atom. So you have atom behavior, which is the same as electron behavior. And the last time we met, so behavior of the atom comes from the behavior of the electron. The last time we met, we were trying to figure out how to calculate the energy of the electron when the electron is going from one energy level to the other. So we figured out the energy first of all in the math, and then we went ahead and figured out the wavelength because the question actually wanted us to figure out the wavelengths. You want to make sure you know the normal units of these different measurements. Wavelengths tends to be in nanometers, so you want to be aware of that. So we're moving on, talking about the wave behavior of electrons. So the scientist who contributed to this information is called de Broglie, and from his experiments, he decided that electrons have wave-like behavior, and he was studying electrons from different points of view. Now, at this point, he calls them particles. Remember, particles is a general term that describes atoms, molecules, the subatomic particles. So he uses the term particles, right? Let me make sure this is, I need to make sure this is recording because I thought I pressed start. Okay, it is recording. I'm usually used to seeing a button here when I'm recording. Anyway, so de Broglie predicted that the wavelength of the particle was inversely proportional to its momentum. So in doing his experiments, he noticed that the electron will have its wavelength, right? We just figured it out. Once you have the wavelength of the particle, this wavelength is inversely proportional to the momentum. So momentum is something that we don't study in chemistry. It's studied in physics, but it's a property that a moving body has. As the electron moves, the wavelength of light it releases somehow relates to its momentum, which has to do with its motion. So from here, we get the relationship wavelength is inversely proportional to momentum has the formula mass times velocity. And then from here, we get this equation on the left. So make sure for de Broglie's relationship, you know this equation right here. In this equation, lambda is the wavelength. So remember, lambda, this is pronounced lambda, like a lamb and then da. This is the wavelength. And then we have h, which is Planck's constant. And then we have m here. Now, his experimental results were not only for electron, but in this case, we're taking his results and applying it to electrons because we're studying electrons, right? M here was the mass of the particle. In our case, it'd be the mass of the electron. So you're going to write here mass of electron. And then we finally have V for velocity. So please notice, in this context here, the V is not frequency. Oops, I just realized something that's in the way. Okay, V stands for velocity. Once again, of the particle, in our case, this is the electron, right? So we're moving on here and applying this equation to a problem. Using de Broglie's wavelengths, we're told here, calculate the wavelength of an electron traveling with a speed of 2.65 times 10 power 6 meters per second. Okay. Okay. So for this right here, I'm giving the speed, and I'm not really given anything else. In this kind of question here, they didn't give you anything else because they assume you know all the other constants. So at some point, somebody sent me an email asking me, do I have to know the mass of the electron? For this kind of question, yes. Okay? Because we have a wavelength equal Planck's constant over, I have seen some books use MC or MV, wavelength equal Planck's constant over MV. Just remember, whatever it is, this right here is the velocity given. So we are given a velocity, right, of 2.65 times 10 power 6 meters per second. So I have this part here done, or this bottom part. I need the mass of the electron. Mass of electron here, they gave me the mass of electron. For this whole, you want the mass of electron in kilograms. So I think it's 9.11, right? It's right here. You want to use the mass of the electron in kilograms, which would be 9.11 times 10 power negative 31 kilograms. Even though in your conversion sheet the mass may be given to you in grams, for this problem you want it in kilograms because the units have to cancel out. And I will show you how they cancel out, okay? So I got the mass of electron, I got the speed of the electron, Planck's constant. Planck's constant, H, is 6.626 times 10 power negative 34 joules times second, okay? So I want to make sure that, yeah. So for this part here, I told you it has to cancel out, right? And in chemistry, when you use numbers and units, the units have to map out to each other. You should see how they can cancel out one with the other. They want us to figure out what in this question. I read through the whole thing. Oh, they want us to figure out the wavelengths. We know that the wavelengths will be figured out in meters first, and then we'll convert the meters to nanometers, right? So in the units, since only meters will remain in the end, that means seconds have to cancel out, kilograms has to cancel out. Somehow the other units that are not meters have to all disappear. So I'm going to write my Planck's constant in a different way. Please note 1 joule is 1 kilogram times meters per second squared. Oops. Hold on a second. Okay. So the way I get the conversion here, you guys will have a conversion sheet, but just in case you're on an exam, like say the MCAT or whatever, PCAT, one of those exams where you have to recall this, the way I remember that is the kinetic energy is equal to 1/2 mass times velocity squared. It's one of those equations you have to memorize. So in the place of the mass, you have the unit kilograms. Velocity is meters over seconds. But since you're squaring it, you're squaring this, and you're squaring this. Kinetic energy is measured in joules, so you put joules here, right? We ignore the half. All I'm doing here is showing you how I remember the units. So I put 1 joule here, I put 1, and I got the equality. So when I was in school, I had to memorize this. I'm just showing you how to memorize it too, okay? From this equation right here. Because it was one of those things where I was like, it's going to be hard for me. So when I have this unit here, you can rewrite it as 6.626 times 10 power negative 34. And then in place of joules right here, put kilogram meters squared over second squared times second. Okay? So let me actually write this over down here so y'all can see. So then the Planck's constant becomes 6.626 times 10 power negative 34. When I work this out, I get kilogram remains, meter squared remains. One of the seconds at the bottom cancel out, the other one remains. So this is what I have. Okay? So now I'm going to plug this in the equation. Wavelength is equal to Planck's constant, 6.626 times 10 power negative 34 kilogram meters squared over second, right? I use this number. This was a means to an end over the mass, 9.11 times 10 power negative 31 kilogram times velocity, 2.65 times 10 power 6 meters. Ooh, hold on a second. I can do better. Per second. Okay. So the remaining second here cancels out with that second. Remember, our goal is to remain with only meters, right? Kilogram and kilogram cancels out. We have m squared. M squared just means m times m, right? One of the m's cancels out with the present m, so we have this m. So we are left with m. Now the math. Multiply all the top numbers divided by the bottom number. Hold on. Hold on a second. I have to find my calculator. Okay. I found my calculator. Okay, the top number, open parentheses, 6.626, exponent, negative 34, to the right, close parentheses, divide by open parentheses, 9.11, exponent, negative 31, close parentheses. Ooh, no. Now you have to enter this just right, to the right, close parentheses, okay? Divide by open parentheses, 2.65, exponent, 6, to the right, close parentheses. Okay, so I end up with 2.7447 times 10 power negative 10. Okay, so let me check to see. Oh, not bad. We got what they got. Now, when we figure out the wavelength, remember the normal unit for wavelength is nanometers. So once we get this, depending on the problem you're working on, if it's multiple choice, if the answer is in meters, you can stop here. If it's not, you want to convert, right? 1 nanometer is 1 times 10 power negative 9 meters. That's what the little n stands for. You work this out, divide the number I still have in my calculator by 1 exponent negative 9 to the right, close parentheses, and I have my answer as 0.2744 nanometers. Okay, so the wavelength is either the top number right here, it's either this number here, or the bottom number. It all depends on how the answer is presented to you. Okay, so hopefully that makes sense. So you're just applying the formula, but make sure this is not math. In chemistry, the units matter. They should matter in math too, theoretically. So you should make sure you convert all the units to the desired unit and then go ahead and work it from there. Yeah. So I guess they just stopped right here and that was it. Okay. After we have done that, we're now being told an electron's complementary properties, the concept of wave particle duality and uncertainty. The idea here is, after all these experiments and all the research, scientists are trying to summarize, kind of put together, consolidate all the behaviors of the electrons. They realize electron behavior affects the behavior of atoms, and we're told electrons' behavior characteristics can be described as the follows. From the particular point of view, remember the electron had two major properties, right? It could behave like a particle. It could behave like a wave, okay? By the way, I didn't give you guys my regular analogy, which I usually use. I understood particle nature of the electron. I could embrace that. The wave part, it took me a little longer, and it's still taking me a little longer to really grasp conceptually and practically the wave part. Okay. Back in the days when you had a phone, a landline phone, you know, you have the phone connected to the wall. I could get that. All the information as far as electrical or waves was coming through the wire connected to the wall or the outlet. That made sense. Wireless phones, I was youngish when it came out, so I didn't really grasp that a lot, at least back at home. Yeah, when wireless phone became available to regular people back at home, I was a little bit like, okay, this is interesting. So we can still get phone calls without the wire. Okay, I can dig that. Then I came to America years later. I saw a wireless printer, and I was like, no way. People are like, oh yay, wireless printer. I'm like, wait a minute. So the printer is printing, but it's not connected to directly to the computer. Oh, we're using a network. What does that mean exactly? Well, where is the wire? There is no wire. Oh my goodness, that bothered me. So the wireless printer bothered me. Anything that was high tech and wireless bothered me. And my friend was like, I don't get why it bothers you. You use a wireless cell phone, right? I said, yeah, but I wasn't really paying attention then when it came out, but now I'm paying attention and I want to understand how is it possible the information from the printer screen or from a computer screen and I see it is showing up in the printer, but there's no direct wire connection. Then I was thinking about, I was doing some research for a whole month. I researched this. This is how special I am. And then I realized, duh, it is the wave nature of matter. So here's the thing. Remember, you have the particle nature. The particle nature is more tangible, the things that you can touch and feel and see. And these are more like the body, right? So particle nature is more tangible. In this case here, this is where you have your wire technology. Okay? And then the wave nature is the part that I would say, from a human point of view, is more intangible. We know there are waves out there, but can you see it with your naked eye? Most likely not. Can you see the wave and the signal? Even your Wi-Fi signal, like right now, look at my Wi-Fi signal here, it's showing you this. And I believe it's working, right? Because I'm getting all the signals, but I can't see any of this stuff. It doesn't mean it's not happening, but you either have the particle nature of matter operating, where you have old school wire technology, or you have wave nature of matter. So as we're going through this, think about that, right? So they're trying to summarize, this is years ago, they're trying to summarize what they have learned. Now, of course, we enjoy the wave nature, right? It gives us freedom. You can have a wireless cell phone. Now your cell phone is a camera. It takes videos. All the stuff comes from the wave nature. And then you have, of course, the particle nature, where it requires you to have physical contact, a wire, and things like that, right? But from their point of view, the particle nature of matter, we saw the behavior of the electron or matter when it had a volume or a mass. So having a volume or having a mass is proof to the scientists that the thing that you're studying has particle behavior, right? They say if it walks like a duck and it quacks like a duck. I don't know if they say it that way, but you know what I'm saying. So here they're saying if it has a volume and it has a mass, we classify it as a particle, right? And then the same object in different conditions can exhibit different behaviors that can have us classify it completely differently. From an energy point of view, if the same particle can now have light that has a wavelength, or the particle itself has a wavelength or a frequency, these are the behaviors that we give only to waves. So if it has wave-like properties, guess what? We say it has a wave nature. So the electron has dual nature. It has both nature. It has both particle nature, depending on the experiment you're working on, where it behaves like a particle. The same electron will also have wave nature. They call this the dual nature of the particle. In the wave, it can behave like a wave. It can give off energy, have a wavelength, have a frequency, etc. The issue, though, is you cannot see both properties simultaneously or simultaneously. If you're studying, depending on the experimental conditions, you're either seeing one or the other, right? So if your experiment only has one condition, you will only get one result, okay? So seeing that, you have uncertainty principle. So Heisenberg uncertainty principle pretty much explains that it's hard to see both the dual nature of the electrons at the same time. So yeah, he's saying here it's impossible to know both the position and the speed of the electron. There's certain characteristics the electron has, but it's difficult to measure them at the same time. So his whole contribution to this is, I am not sure that you can actually measure both of these characteristics of the electron at the same time. If you try to measure its position, you're successful, but then you sacrifice the speed. You can't measure the speed. If you try to measure the speed, you can't figure out its position. The electron is in constant motion, so it makes it so difficult to get all this information. Okay? So moving on then, we finally get to Schrodinger's equation. If you ever watch Big Bang Theory, or if you read about this somewhere else, the Schrodinger's cat, the whole idea of this one here, there's a whole movie that came out of this. I actually watched it recently, last year, during the time of, Corona, the beginning of Corona. I ran into it, you know, and I was like, very interesting. It's a very deep movie. But Schrodinger is a scientist who goes out of his way to say the behavior of the electrons, the wave behavior and the particle behavior usually can't be seen at the same time. You either see the one behavior or you see the other behavior. But he says that, now all of that is not written right here, but he essentially says when we, the scientists, are not studying the electron, both behaviors exist. So, like, if you leave the electron in its own home in the atom, then both the wave and the particle natures exist. But once you, the scientists, go in there and try to measure one thing, depending on the conditions of your electron, you either choose one side or the other, but you never get to choose both. Some deep stuff, right? So you either pick one side or the other. So the movie I was watching, essentially, it's a sci-fi movie. So sci-fi movie, they can go wherever they want to go with that movie. They were just essentially saying that the same thing happened with people and their personalities. That you can have one personality or the other depending on the conditions. I don't want to give out the spoiler, but the point was conditions happened to where Schrodinger's equation worked out to where dual personalities of the same person met with each other. So it was like you and another you, and they weren't ever supposed to meet, but then they met in the movie. It was crazy. But yeah, anyway, back to the lesson. The point is the wave nature and the particle nature for us humans, we can never experience both. So even though we know in the atom both exist, when we start to interact with the atom and the electron, we are only able to observe one or the other at one time. Okay? So from Schrodinger, we essentially learn about what is called the orbital. So we're graduating from the orbit to the orbital. Let me remind you guys of the orbit real quick. The orbit is what Bohr talked about. Bohr said you have a nucleus in the middle, and around the nucleus you have these specified orbits that are around where you will find the electron. And the electron was stuck on the orbit, kind of like a car stuck on a highway. They can't really get out. But then until an outside source of energy came into the electron will absorb the energy and go to a higher orbit. Oops, hold on. Go to a higher orbit, right? But once it gets to the higher orbit, the excited state, it had to come back home. That was what Bohr was talking about, that orbit. Now we are graduating from orbit and looking at orbital. So how is the orbital different from the orbit besides the fact that you have an A and L? We're told that from Schrodinger, he was able to produce an equation that helps scientists figure out the wave function. The wave function, which is essentially chi squared, is a probability distribution map of a region where the electron is likely to be found. Okay, so one of the things I do with my phone, I have an Apple phone. One of the things I do, I try not to share my location, right? I try, because I heard that there's a security thing with that. So I try not to constantly broadcast my location. I'm like, so when I go into an app, they always ask me, you want to share your location? I'm like, no. Do you want to share your location while you're using the map? I'm like, okay. If it's Grubhub where I'm ordering food, I guess share my location. I guess it kind of helps for me to know what food I'm ordering in the neighborhood, right? So I'm like, only share while I'm using the app. When I'm not using the app, I don't want you to know where I am, okay? You don't need to know it. So imagine all these apps trying to know where you are. So when Schrodinger was doing his work, one of the things that he did was draw a probability map. This is a map where there's a very high chance to find the electron. Remember, the electron, wherever it is giving off signal, kind of like our phones give off signal of where we are, right? The electron is giving off waves. So you can actually track where the electron is, and like the phone companies do, and Facebook does, because it really does, right? You all know that. Anyway, the probability distribution map is the scientists working so hard to find where the electron is. And once they draw where the electron is, everywhere the electron has been, the scientists assume the electron will be able to go back again. So we'll talk about these maps right here. Let me kind of zoom out and show you guys what they end up looking like, because our goal is to talk about these maps in detail, okay? So I'm showing you the last slide. After all the work he did, the orbital, the specific orbital, depending on the electron and where it was, had these shapes right here. Okay, right now because of corona and everything, I don't move around a lot, but I used to travel around a lot, and my map will be a weird one because I'll be all over the place. But remember, this is a map, right, that shows the possible location around the nucleus where the electron can be found. So what we call the orbital would just be a 3D area, or you can call it a region around the nucleus where the electron is found, right? So as scientists work, they're trying to find out where the electron was. I'm going to focus only on the S1, the S orbital, and then for every point they found the electron, they put a dot. Kind of like trying to find catch a fugitive, right? You know, on the police boards, they have a dot. Oh, he was last seen here at 3 o'clock in the morning. Now he's here. So they're trying to look for the electron. Where is the electron? Where is the electron? And then put a lot of dots, and in the end, kind of step back and say, wait a minute. This dot looks, oh, I shouldn't have put a dot in the center because the electron is never found in the center. Oops, that was too big. You all know what I mean, right? Except for the center. The electron is found all around in the atom, but not in the center where the nucleus is. So they stepped back and said, wait a minute. These dots form a shape, and the shape is round, it's spherical. So the electron is found, if it's in the s orbital, it's found anywhere in the atom except for the nucleus, of course. It's not found in the nucleus, but it's found anywhere in the atom. And so the shape where the electron is found anywhere in the atom, if it's the s orbital, is called spherical. Okay, so if our bottom line is to learn these shapes, why all this dialogue between the shapes and where we were? Because it's kind of like a puzzle. It's very systematic, right? So we have to learn the rules, as you can see. Remember, I showed you our goal and our objective. Our goal, now that we've learned that the electrons are in orbitals, not orbits, right? It's a 3D region, not a flat road. It's like a whole 3D area where you find the electron around the nucleus. We're now going to learn the skills required to locate the electron the best we can, okay? These are called quantum numbers. So we are finally at the quantum mechanical model. In the quantum mechanical model, this model uses 4 quantum numbers. Okay, so bottom line, 4 quantum numbers are used to find the location of electron. And when I mean location here, the best thing I'm talking about here is the orbit, right? To try to figure out which precise orbit does the electron live in. So once again, trying to relate this to us, it would be like somebody trying to triangulate to find maybe where you live, your location. Maybe you're transmitting a signal, right? But only in this case, we're using these 4 numbers, 4 quantum numbers versus GPS locations to try to locate the electron. If it was you, or say your car or something, they'll be using GPS technology to try to find you or your car or your technical device, right? So similar idea, similar practice, but not the same thing, okay? So these 4 quantum numbers are important for that. What are these quantum numbers? The first one is called principal quantum number, and the symbol is N, okay? And you know how you have your formal name, or even, okay, let's stick with COVID. Okay, you know how there's Corona and then there's COVID-19. There's the formal name and there's a kind of like the casual name. So here with some of these quantum numbers, you have formal names and then you have the casual name. So principal quantum number is the formal name of the first quantum number. Its casual name is energy level. Doesn't this kind of sound familiar? Yeah. We last saw this with Bohr. Bohr was the one who came up with the principal quantum number. So in the world of science, this is how things work. Most of the work that somebody does is usually not original. It's inspired by somebody else's work, right? It's usually inspired. So somebody does something and then it sparks interest in you and you're like, I want to investigate this further. Then as people are doing more work, they're adding on to somebody else's work. So in the end, when someone is publishing their work is not just their work. It's kind of like their work, other people's work, a remix of other people's work. So you're putting in so many other jobs together to present your work, right? And that's just how science works. So in the end, you cite, oh, I got this work from this person. So the energy level really is not original to this quantum mechanical model. This came from Bohr. So we're giving him credit. We're giving him a shout out. Came from Bohr. Okay. He was the one who said there's so many different energy levels in the atom, like different roles in the hall of a concert. Some of the energy levels are close to the nucleus, some are far away. Remember how we had the nucleus, and then we had what is it called? The planetary model. You had all the orbits around them, energy level 1, energy level 2, and so on and so forth. That was first put together by Bohr. So we give him credit for that. Over here, though, we add the term principal quantum number, the symbol is N. So make sure when you're studying, you know the formal term, know the casual term, then you make sure you know the symbol, okay? You do have a lab that has you go through all this. Number 2, angular momentum. And this is a quantum number with a symbol L. What does this give? Well, it gives us the orbital type. In this context here, you all saw that last slide I showed you, right? There's so many different types. What are we talking about? The one in the first layer, the second layer, the third layer? We don't know. So this quantum number here will specify the type. Okay. So once again, as you're taking notes, write the name angular momentum. Oh, angular momentum is also called the azimuthal. It took me a while to learn how to pronounce that. Azimuthal. Okay. If you see the term azimuthal or angular momentum, don't panic. It's the same quantum number. The symbol here is L. And we'll talk about the restrictions, okay? This one tells you the type of orbitals. Now, with Bohr's model, he didn't need type because he only saw one type. He only saw round, right? And everything was round. There was big round, small round, really, really small round, and really, really big round. And then the third one is called the magnetic quantum number, M sub L. Okay? And this tells you the specific shape of the orbital in reference to the X, Y, and Z coordinates or plot. And once again, we'll go through all of this in context. Right now, we're just going over the overview, right? And then number 4, our final one, is called the magnetic spin. Technically, magnetic spin is not covered much in this chapter because you know how scientists are. They're like, well, the magnetic spin was not covered in this era, in this time, so you learn it later. Let me tell you something. Because your lab has you group all these 4 together, we're covering them all together, okay? Even though later on we'll cover magnetic spin again, we're covering all 4 together. But while we're here, let me mention this. The first 3 quantum numbers, so the first 3 quantum numbers specify. Specify is the term they use. I like to say code for, like it's some kind of program. They go to a specific orbital. Specify a specific orbital, right? So it'd be like an address, a street number, a house number goes to a specific house, like an address. The first three quantum numbers end up specifying a specific orbital. Okay, so in my head, to make sense of this, I think of the orbital like a house versus the orbit like a street. Okay, so our goal is to try to figure out which house, which orbital does this electron live in. Okay, you will use the first quantum number, n, principal quantum number, the azimuthal or the angular momentum, and then the m sub l, the magnetic. These three here will give you the orbital. Okay, if the first three give you the orbital, what does the m sub s give you? The m sub s does not tell you where the electron is. So technically it's not part of the whole let's go find the electron, but it tells you once you find the electron and you look inside that orbital, what do you find? You're able to find the orientation of the spin of the electron. Okay, so let's try to relate this once again. So what does the magnetic spin mean? In general, electrons are constantly in motion, and there are two possible spins. One is clockwise. Hold on a second. Let me think of clockwise is like this, right? So you have clockwise, and then like this, counterclockwise. So these are the two possible spins of the electron, right? The electron can either go in the clockwise direction as it spins, it goes around, or the counterclockwise. So once you find your electron, which one is it? Is it clockwise or is it counterclockwise? Because it does make a difference. And that's what the magnetic spin literally tells you. Clockwise spin, counterclockwise. Okay? So let's go ahead and learn each one step by step. So what I'm going to do here is, as we're going through the quantum numbers, I am going to use the periodic table to help you remember this. When I was going to school, oh my goodness, this section right here, I was like, the teacher did not rely on the periodic table a lot to teach this. He or she, actually they're mostly he, to be honest, they were mostly he's. So he just mostly just went through the text and then said stuff, and then you're sitting there going like, oh my goodness. And then you memorize it and you hope for the best. But the periodic table can be a tool to help you remember. Okay, so we're back to the first quantum number again, principal quantum number. This tells you the energy level of the electron. It says here it characterizes the energy of the electron in a particular orbit. It is the Bohr's energy level. So here we're giving credit to Bohr. We're giving him a shout out. Hey, Bohr, thank you for your work. We're taking your work and we're moving it to that next level. Energy level. I'm sorry, y'all. I know I'm corny and I have these weird jokes, but that's what helps me keep this stuff alive, right? I have to teach this every year. Anyway, so now the principal quantum number, once again, as we go through this, I'm going to try to keep some kind of focus here. We're looking at four different things. Make sure you know the names. So for the quantum numbers, I'll say here, for the quantum numbers, which you will see in your lab also, right? Number one, know the name and other name if there is one. So this one here is principal, okay, principal quantum number. The other name, energy level. Okay, so we know the name, we know the other name. Information it gives. So in this context here, it gives the energy of electron or orbital. Okay, it gives the energy of electron or orbital. And this is additional information because it's not the primary information. Additional information how close or far electron is to nucleus. Okay, remember, when the energy level is high, the electron is far. When the energy level is low, the electron is close to the nucleus, right? So far electron is like that nosebleed section in the hall, the cheap seats. Close to the nucleus, that's more like, what do they call that? Good seats. I can't think of that term right now. Yeah, the front row seats, that's where if the athletes are playing, they throw shirts at you and you actually catch them, those seats right there. Okay? So I'm trying to make sure I have all this. And then you want to know, besides that, you want to know the restrictions. So the restrictions here, they tell you that the values of n, so you need to know the letter too. The value of n can be any whole number that is greater than or equal to 1. So I should say the letter before the restriction. The letter or symbol, which is n, and then the numbers or values. I should say here possible values. So they say it can be any number that's bigger than or equal to 1, right? So n can be bigger than or equal to 1, i.e., n can be equal to 1, n can be equal to 2, n can be equal to 3, n can be equal to 4, n can be equal to 5, all the way to infinity. They didn't give us a stopping point. Just start from 1 and go, right? So go as far as you can, yeah, from 1 to wherever. But n cannot be less than 1, n cannot be a fraction. Okay, so as you guys are working on your lab this weekend, I think it's your lab for this weekend. You can start working on it. Don't wait till the last minute to work on that, because you want to know this, prepare for the exam. Okay, 1, 2, 3, 4, 5. Does anybody have any question? I know I've been kind of going on, but remember, if you have a question, you can feel free to type it in the message box, the chat box. Okay, so what else? I want to make sure. So we got the letter N. We got the values 1, 2, 3, all the way to infinity. So we're told here the larger the value of N, the more energy the orbital has. The larger the value of N, the larger the orbital. So here's the other thing, the picture I want to give you. I don't know if y'all know about Russian dolls. The Russian dolls, I think that's what they're called. They are usually like a tiny doll inside a bigger doll, inside a bigger doll, and stuff like that. So you have these dolls inside of each other. And so the idea here is the orbitals are inside of each other, like concentric circles, meaning the small one is inside a bigger one, inside a bigger one, inside a bigger one. So as the energy levels increase, so must the orbital, because it has to hold all the other orbitals in front of it. It's like outside, right? So logically, as the energy level increases, so does the size of the orbital. Okay? Okay, what else? Oh, so here, for this part here, for right now, you just kind of have to watch me do it, you know. This is using the periodic table to show you the energy level. So, as it says right here, periodic table showing energy level. Remember, when we are done with this, let me kind of give you the goal of this. We will use 4 quantum numbers to find, actually I should say 3 first. 2 quantum numbers to find position of the electron for the specific element. Okay? The last quantum number will provide the spin, the magnetic spin. Remember, clockwise, counterclockwise, to the left or to the right. Okay? The first 3 quantum numbers help us to figure out the position of the electron for a specific element. Well, this is the one thing I want to mention right now, and I hope as I'm writing this down, y'all are writing this down. The element has the quantum number of the last electron. I'm trying to make this simple, but I feel like by oversimplifying, maybe I'm making it more complicated. But you know how elements tend to have a lot of electrons? So if it has all of the electrons, it can't have all quantum numbers because all the electrons live in different locations inside the atom, right? So the element, aka atom, will tend to have a quantum number that matches, I should say, that matches the quantum number of its last electron. Okay, it has to be its last electron. So hopefully this makes sense. You have an element, it has many electrons, so which one does it pick? You know, because the electrons are in different size, different energy level within the atom, it picks the last electron. Okay, so when we're looking at, we'll come back and examine this some more when we're actually putting this together. When we look at this right now, we're looking at the periodic table. We're trying to figure out from the periodic table, what are the energy levels? Now, right now, I have a blank periodic table. It doesn't really have, elements in here. So we're told this is energy level 1, from left to right, energy level 1. You can see that right here. N is equal to 1. N is equal to 1. Oh, by the way, in the regular periodic table, you have helium here. For this purpose here, we moved helium from here to the left. Okay? For the purposes of quantum number, helium technically rooms with hydrogen. So this is, this right here is helium. This is hydrogen. Okay? This is energy level 2. Energy level 2 appears on both sides. Here and here, energy level 2. So what I would do is, I think I have a blank periodic table. If not, let me write myself a note, add a blank periodic table to give you guys a chance to write this out for yourself. I mean, you can print it out, but I feel like writing out for yourself is more useful. So add blank periodic table. I think I have one on there for you guys to, or you can print this out and you can go ahead and just fill it yourself. Energy level 3 here, energy level 3. Remember, these are figured out experimentally because when we get to the 4th row, the 4th period, look at that, energy level 4. All of a sudden, energy level 3 is kind of like it dropped a level a little bit coming down here, but these are figured out experimentally. Energy level 4, down to energy level 3, back up to energy level 4. Okay? Here we have energy level 5, down to energy level 4, back up to energy level 5. If this is not necessarily making sense, don't try to overthink this because remember, we are designing a tool to help us accomplish a task. And this is the task I told you about. It's like you designing a ruler, which a ruler probably made more logical sense than what we're doing right now. When we get done with it, when we're using it, it will make more sense in context. Okay? To make it easier here to figure out how this goes, what I'm going to do is I'm going to color this section right here, and we'll look at this section first. So from top to bottom, we're going n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is 5, n is 6, n is 7. Hopefully that makes more sense, right? Now use a different color. What color do I want? Blue. For this part here, as I said, now I'm going to this section right here. In this section to the right, this box to the far right starts at one less level than the one to the far left. So it starts at energy level 2. And this whole row from here to here is energy level 2. Energy level 3 from here to here. Once again, from there to there. So we're going across, right? Energy level 4. N equal 5. N equals 6. N equals, oops, not 6 twice. N equals 7. Okay? So there's some kind of sequence to this. So as you're going down, you're increasing the energy level by 1 in the same region. So please notice I have the red region now. I have the blue region. Now I'm gonna do the energy levels for the central part here. I will use the color pink. Okay. For this part here, due to experiments, the N starts at energy level 3. So energy level 3 goes all the way here. Energy level 4, energy level 5, energy level 6. I'm not going all the way to the end because I'll show you what happens here. Okay? Then I have my final part, which is here. See this little star here? This little star just means a detour. When we're going through the energy levels, we get to energy level 6, we'll detour down to this, go all the way here, then come back here. So I'll explain all that stuff when we're doing quantum, what's it called? Electronic configuration. We're not doing that just yet. So for this, I start with energy level 4, and here energy level 5. And this goes all the way to here, all the way to here. Now, it may sound a little complicated, but imagine this was a concert hall, a weird concert hall. Sometimes I think about things I would do if I had lots of money, okay? And there weren't world problems, so I didn't have to spend my money dealing with hunger and stuff like that. Just money to, like, say I was like Jeff Bezos. Ooh, I need a moment. Yeah, and I was very, very rich. And there was something I could do. I would actually like to get a concert hall and design it based on these energy levels. It would be like a nerdy concert hall. And when people are coming there and they buy tickets, they're asking them, what energy level do you want? Ro, we don't call them that here. Anyway, listen, that don't make sense. Yeah, yeah. Anyway, so people could find different concert halls or whatever, or their seats based on the energy level. So you had to find, well, go to N2 and you're like right here or right here. But in the one with the red, and so you have to go to this part right here. And we'll go into how you can tell which N2 we're talking about. The one on the right or the one on the left, right? I mean, correct. So please notice, with the one on the right, or the one that's red, when I started labeling this, I started with N is 1, right? That was the smallest level. The one with the blue is what comes next. With the one with the blue, I started off with N is 2. You see that? The one with the pink, I started off with N is 3. The one with the green, I started off with N is 4. So when it comes to the order, we kind of see the same thing, okay? So for right now, all I did was show you how to figure out the energy levels based on the periodic table. So since we have this right now, I continue just yet. I want us to detour just a little bit, and we'll practice this. So hold on a second. I just thought about it. Let me see if I can find a periodic table here. Table is like I can't write on it because it's on the internet. Okay, so remember how starting with this block on the left here, these two, it starts with N is 1 and it increases by 1 all the way down, right? So let me try to minimize the screen a little bit. Oops, I just did the opposite and I maximized it. So I want you guys to help me with this part because, so I'm moving these out of the way so I can see you guys' answers. So as I said, type here, right? We're going to do a little review to make sure we're on the same page. Remember the one on the left, so eventually we'll call it the S block, the one on the left. It starts with N is 1, N is 2, N is 3, N is 4, N is 5, N is 6, N is 7. For the N is 1, remember helium technically belongs with hydrogen. So this one here starts with N is 2, N is 3, N is 4, N is 5, N is 6, N is 7. This middle block here, since this started with N is 1, this one here started with N is 2, This one here starts with N is 3, right? So N is 3, N is 4, N is 5, N is 6, right there. And then this one over here starts with N is 4. So N is 4, N is 5. So I'm going to give you guys the name of an element, and I want you to tell me the energy level. Okay? Let's start with this. I'll start with an easy one. Hydrogen. So hydrogen is right here. Okay? What do y'all think the energy level for hydrogen is? 1, right? Yeah, right there. Okay, that was our warm up. We're going to get a little bit more interesting. Germanium. Yes, N is 2, N is 3, N is 4. Very good. Gadolinium? This one here. GD. I don't know, can you see my mouse? Yeah, it's GD. Yeah, that one. Also 4, right? Because remember, we started off with 4 right here. Very good. And then for this one here, zirconium. You know how they use cubic zirconium as a artificial diamond, a knockoff? That element right there. Apparently, I really, really like 4. Okay. Okay, but you get the idea, right? So for these elements here, depending on the element, its position, we can give its energy level, right? And we are only referring to the last electron, not the other many in the element, right? Thank you very much, Victoria. So yeah, magnesium is energy level 3, calcium is 4, strontium is 5. But when you go over here, ruthenium is 4, right? Because it's 3, 4. And then here, selenium is 4. And over here, where's my best one? Californium is 5, right? Okay, so we're done with the first quantum number. We're gonna go back. Does anybody have any questions about this? Okay, so with no questions asked, I'm just gonna assume no questions. So we'll come back and put it all together. Hold on, this is right here. I need to rearrange all my slides. Right there. So once we have learned the 4 quantum numbers, now we are, sorry, just the first one of the 4. Now we are moving on to the next one, the azimuthal quantum number, or what we call the angular momentum. With the angular momentum quantum number, what we're trying to say is, okay, Bohr did some good work where he was able to figure out that the orbit was round. But scientists at this point were like, but there's more than one shape. It's not just round. Some are round, some are figure 8, some look like a clover leaf, some look like what I call a flower. It's really 8 bubbles, but I call it a flower. Okay, so it's kind of like each time you're going to the next shape, it doubles. Right here, you have 1 circle, 2 circles. You double that, you get 4 circles here, you get 8 circles, something like that. So there's all these sequence, right? All these relationships. So they're like, wait a minute, how did Bohr only see 1 when we see all of this? The work in science never stops. Bohr was a man, well, he was a man ahead of his time. He had more older technology instrumentation. So he was only able really to see the first one, and he wasn't seeing it, the whole thing in 3D. He was only seeing it flat. So all the work he did, one of the things that they say later on, that the, how should I say, I can't remember words this morning. Not this is a disadvantage. Where Bohr messed up is Bohr said that Bohr's model only works for hydrogen. Because his model, even though it was so great, the planetary model, who doesn't like that one, right? It only worked for hydrogen because hydrogen in this case was the only element that has 1 electron and only 1 electron in the s orbital. All the other ones have more than 1 electron, so it does get complicated. So Bohr's model is great, but it only works for hydrogen. So if we didn't have other elements, will be satisfied with his work. But the quantum mechanical model gives us more information when we look at the other elements. Okay? So over here, we're told that there is more than one shape, one general shape. How do we know which is which? So over here, the name momentum or azimuthal quantum number. So going with the name first. The letter is L. So let me add the little bottom so I can kind of sort through this. So the name for the second one, momentum. Okay. And then kind of like the pet name, azimuthal. Azimuthal quantum number. Okay, the symbol is L, or the letter. So I'll say symbol or letter is L. Now, the possible values here, there's an equation for it. They say the from 0, it can be bigger than, what are these people doing? My neighbors, all the way to n minus 1. So the possible L value will always be one less number than the n value, okay? I don't know if I wrote this correctly. Let me see how they put it here. Right, from 0, yes, it's equal to 0, but it's equal to or greater than 0, all the way to n minus 1. So this is how they wrote it. I think this is probably better than what I wrote, right? So L can have an integer value. Once again, you cannot have L that's like 1.5 or whatever. It has to be a whole number, an integer, right? From 0 to n minus 1. What information does L provide us though? It tells us about the shape, the general shape. I call this the general shape, okay? So the angular momentum quantum number determines the shape of the orbital. So information, I call this the general shape because you see how there's a more specific shape. The general shape of orbital. Now, even though you can have all these many values of L, really we only work with mostly 4 because the information we have is limited. So yeah, we know L can go to 1 less than infinity, but we just deal with 4. And I forgot to mention this with N, even though it can go to forever, the experiments we have right now and the results we have right now, it maxes out at 7. But technically, we can have up to infinity numbers. We just haven't discovered them all. This is where y'all come in and you do some more work, and then you publish more books and you make chemistry even more fun, right? Yeah. And make the periodic table even more complicated. But for right now, all we know based on the experiments we have is n equals 7 is the highest one that we know. Even though we know it can go to infinity. We just haven't figured it out. And beyond. I had to say that. Okay. Yeah, it's a general shape. So here, with this part here, it gets a little complicated because they do have both letters, S, P, D, F. And then they have numbers that go with that. So I'm going to just talk about the 4 shapes again. So the shapes, I'm going to draw those here. Then the letter, and then the number. Because remember, these are 4 quantum numbers, not 4 quantum letters. But depending on the context, scientists use one or the other. And that's the part that used to kind of frustrate me as a student. I'm like, if we're going to learn numbers, can we stick with the numbers first before we digress? But as soon as we got into it, they were digressing and going to all these different places. So I'm trying to sort this out so you can see. Most questions ask you for number, this part here. But they may ask you for letters. So you want to be prepared to know number, to know letter, and then, of course, to know the shape and how they connect with each other. So I told you, the general shape, you have one that's round, one that's like figure 8. So it really looks like 2 round circles connected together. The other one that's like 4 circles. They call that the clover leaf. I almost want to add a stem there. It's not really a leaf. It's just like that. Then the last one has got 8 leaves or 8 circles together, I just call it a flower because it looks like a flower. 1, 2, 3, 4, 5, 6, 7, 8. Sorry. Forgive me for not being an artist. This is just my best. Can you imagine? I thought I was a good artist when I was younger. I don't tell little kids you can be anything because I'm like, obviously, right? Look. Okay. Here. I'm like, do your best. Do your best. Okay. For this is called spherical. The letter that goes with that shape is the letter S. The number that goes with that shape, to describe that, the number that goes with that is L equal 0. So if the electron lives in the S shape or spherical orbital, you can say the electron lives in the L equals 0 orbital. Or sometimes they'll just say in an S orbital. And so here's the issue is early on, they will start referring to this. Oh, the electron was in the S orbital and you haven't even grasped it yet. And you're like, wait, hold on, slow down. So I want you to relate these three to each other. The S being spherical just means round. The letter used here is S. Sometimes they can call it just the S orbital. And then the number is going to be 0. L is 0. When the two circles like that, it's called figure 8 or dumbbell or figure 8. Okay. And the letter here is P. So sometimes it's called P orbital. Okay. So figure 8. Now remember, Bohr only saw the first one and it wasn't even spherical. It was flat, 2D. And for this one here, L is 1. Okay, so you see how it all tied together. Okay. Any questions about this so far? Hopefully you're following along, right? Then this one here is going to be clover leaf. And this is D. Sometimes called DU, D orbital. For this one here, L is equal to 2. And this one here doesn't really have a common name, so I call it flower. I'm like, wait, how come other people can name these other ones? Why can't I name that? So I just call it flower. A better looking flower than what I have here. And it happens to be called the F orbital. And for this one here, the value of L is equal to 3. So remember, these quantum numbers code to those shapes. The first quantum number tells you how close the shape or the orbital is to the nucleus. Quantum number 1, N is 1, very close to the nucleus, like very, very close. N is equal to 7, very far from the nucleus. L is 0, the orbital is round. L is 1, the orbital is that figure 8 shape. L is 2, cloverleaf shape. L is 3, looks like a flower. Okay, so let's detour again and look at the periodic table because our goal is to learn these, but the context is, the elements. We're trying to apply it to the elements, right? So let's go ahead and apply these to the elements. So periodic table somewhere here. Oh yeah, it shows them right here. Remember how I told you guys for these purposes, let's move helium over, relocate helium over to its roommate, hydrogen. So helium, we move it from here over here. At some point in your lab, you'll be asked to draw the blocks in the periodic table. You can go ahead and use these blocks. If you want to leave the helium over here, that's fine. Just make sure that you use different colors to indicate the blocks, and then make sure the helium block matches the remaining of the S block. Okay? So in my analogy, I was using a concert hall, right? And the different seats and different numbers. Let me see if I can stick with that. Usually by this time I move to a neighborhood because we're looking at little rooms. Now imagine, right, with social distancing, I actually saw this online where some countries were going a little extreme. Maybe it was helpful. I can't tell. I really haven't read the stats. And when all the social distancing things happened, people wanted to go out and eat. I saw this online. I don't know how true it was. There was some restaurants in Europe or whatever where they had little, I can't really call them cubby hole things, but it was like they had a table at a restaurant outside with two chairs, and then there was this enclosure around the table and the chair to protect the couple from the people next door. But it was kind of clear, so it's like a pod, right? So it was, you're dining in a pod. You're not suspended in the air, but there were these pods being placed around the chair to give you ultimate social distances from the person next to you. Now imagine, okay, I'm trying to use what's going on right now to bring it to the lesson. Those pods were now translated to my hall. Remember, the S block has only S orbitals. So I'm going to try to fill this right here. Okay, this is me trying to be creative on the spot. If you happen to be in my hall, I'll call it the periodic table hall, okay? And you happen to get your seat in the S block, all these seats right here are going to have pods that are spherical shape. Oh, sorry. We have to go with the order, right? So a small sphere, a bigger sphere, a bigger sphere, right? Because I'm going down in the energy level, an even bigger sphere, and the bigger it gets. So they're all the same shape. They're all spherical. But as I go down the road, the energy level, it has to get really big. I should have started it very small, but you get the idea, right? All the elements in the S block have the same shape. Round, 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 or spherical. So it tells you L is 0 corresponds to the S block. Don't forget the energy levels. We said earlier that as the energy level increases, so does the size of the energy level or the orbital. So this should have been very small so that the last one is very big. And each time you go down the energy level, it gets really, really big. Okay, this is all, I mean, the concert hall and everything is all fictional. It's all in my head. Then when you go to the P block, this part actually gets more complicated because there's one more quantum number I have to show you guys. But over here, I'll just show the first row. In the P block, let me go with this first row right here. I will go with the, actually, let me do the middle one because it makes it a lot easier. I'll go with this P right here. So if you get the P block, this is what the shape or the symbol on your orbital looks like. This shape, this shape. And it gets bigger when you go down the energy level. It gets bigger, gets even bigger, gets bigger, gets very big. I tried, okay? The D block, once again, I'll draw the middle one. 1, 2, 3. I'll draw this one here. And that will be tiny one, bigger, bigger, bigger. You get the idea, right? The different shapes. So imagine you're sitting there looking at everything together. And so, of course, if you have a preference, in this case, you pick the experience you want. Do you want to be in that shape or this shape or that shape? With the F block, once again, that one was a complicated one, but you get the idea. I'll just pick these right here. That'll be a small flower and a really big flower. Okay? So remember, all the elements in the S block, these are all spherical. All the elements in the P block, they are all figure 8. The ones in the D block, they're mostly clover leaf. The last one, I'll show you the specific shape when we get to that quantum number, the next level. And then this last one here is going to be mostly flowers. Okay? So let's go back to our periodic table. Then I'll give you a moment. Either you're writing this down somewhere, capturing with your camera, because y'all do funny things with notes these days. And we're going to go back to our periodic table right here and apply this. So as usual, I'm going to click on different elements. Hopefully you can see my mouse as I'm swirling around here. And then you will tell me the letter first, and then the letter or the number. I think I didn't really do, oh, my bad. I didn't do a lot with the numbers, did I? For this one here, for the first one, L is 0, L is 1, L is 2, and then this one here, L is 3. So if they ask you for the numbers, I gave you the letters and the shape, right? But L is 0, L is 1, L is 2, L is 3. And you see the order I'm going? Because that's the order that they work with. From here to here to here, then to here. Okay, L is 0, L is 1, L is 2, L is 3. Okay. Man, as I'm looking at this idea, I'm thinking, I can do this. Only I forgot the part where I don't have money to do this. Ah, okay. I can dream. I can dream. Here. Okay, so we'll start small again. Let's start with hydrogen. So for hydrogen, what is the letter for the orbital? Give me the letter and then give me the L value. Anybody? What's the letter for hydrogen? Oh, okay, okay. Well, so right, thank you for that. So you gave me the two quantum numbers, right? L is 0, N is 1. Don't forget, for L is 0, that's the S block, right? Okay, you gave that works. Yes. So if you were going to do it that way, you want to write the N first and write the L second. So you want to write N is equal to 1, L is 0. Okay? Yeah, but thank you. That's way more than I asked for. Yeah. N is 1, L is 0. Okay. So let's see. Let's go with right here. Aluminum. Since she started this, let's go ahead and do both, right? Do both the N number, then the L number for aluminum. So N first and the L second. Okay, remember, but back to the N. Want to get the N value first. You know what that is, and then you want to do the L value. And in the end, of course, I'm going to give you guys a periodic table that I think it's already on there, because I think it's really already on there, where it kind of helps you find these things out, so that way it won't be as complicated. But right now, I'm trying to get you to engage and get you to think about it, you know, because when you have too many resources, it forces your brain to be on power save mode, and the point is for you to engage. For the N, this was 1, 2, 3. So aluminum, this is N is 3. And then this whole block, this whole section, this area of these seats will be L is 1, because it goes from L is 0 for this area right here. Then this is L is 1, then L is 2, and L is 3, right? So it's N is 3. So where helium is all the way to the left, that's 1, 2, 3. So N is 3, L is 1. Yes, yeah. Okay. Yay. Good. Okay, let's do another one. Let's do another one. Palladium. No, 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 let's not do palladium. Let's do platinum, okay? So apparently white gold is like, oh, white gold. Now we're going platinum. Okay, so this is platinum, the one they talk about. Whoa, Manuela, hold on a second. Okay. Okay, hold on. So for this one here, N is 3, N is 4, N is 5. Very good. Yeah, I'm a little slow like that. Okay, yes. N is 5 for platinum. What about L? What L is this? Very good, guys. So we got the N down, right? I think we're getting the hang of the N. Yeah, this is 3, 4, 5. Remember, the L is 0, L is 1, L is 2, L is 3. Yeah, yeah. I mean, you gain the hang of it. You just need some practice. Once you have practice, we'll work on some more on these on when is it? On Wednesday. Yeah. By this weekend, y'all will be pros at this. And when you do your homework too, People actually hate this section here. I'm like, what are you talking about? To me, this is like a puzzle. Somebody said it was like Warcraft. I'm like, I don't play those kind of games. I don't know. This is like a game to me, you know. Yeah, but you get the idea, right? So now we can code to 2 of the 4 quantum numbers. We can figure that part out, right? So if I say, oh, let's not do gadolinium again. This sounds like some sci-fi stuff. Californium right here. Californium. Californium, this level started at 4, right? So N is 4. N is 5 where californium is, right? N is 5. And L is 0, 1, 2, 3. Okay? Yay, we're doing good. Let me talk about the last quantum number required to specify the orbital. Then we'll do the one with the magnetic spin. We'll do that on, when is that day? Wednesday. We'll do that on Wednesday. So by the time this part here will be more, yeah, it'll be better. We're hitting my goals. My goal was to make sure we went over this at least twice. Okay. I don't want to do the questions just yet. I'll have to say, please work on Wednesday. Okay. So I have to remind myself I'm skipping the quantum numbers, or at least the questions. I want to cover this before I let you guys go. The magnetic quantum number, that's the 3rd quantum number. Remember I told you guys it marks the specific shape. Yeah, we have the general shape, but not all the shapes are the same. So the magnetic quantum number, this is the position or the orientation quantum number. So in the world of chemistry, positions matter and so do orientation. So we have to specify, because in the world of chemistry, oh, the sun is coming out. That's interesting. They did say it was going to come out, but it's very cold out there. The orientation of the orbital makes a difference because chemists believe that the environment of the electron or the orbital can make a difference, that the environment can be different. If the left side is more cold than the right side, that's completely different, right? So we have to specify the environment or the orientation of the orbital. For that being the case, it says the magnetic quantum number is an integer that specifies the orientation of the orbital. The direction in space, the orbital is aligned relative to other orbitals. So it's like when you're looking at one orbital versus the other, are they pointing at the same end? If not, they have to be treated as differently or different from each other. So for this one here, we get integers from negative L to plus L. You know what we can do on Wednesday also? I was just thinking about that. We can work on some of the questions in your lab since it relates to this topic right here. So for this part here, I'll just give you guys some example. When L is equal to 0, the previous quantum number, then we can figure out the value of M sub L. M sub L will be equal to 0 because we're told here it has values that are integers from negative L to plus L. We need the value of L to know what M sub L is going to be. When L is equal to 1, M sub L becomes negative 1 plus 1. We don't just have one possible value of M sub L for the same value of L. We have as many as needed. So they show you right here, possible values of M sub L start from negative 0, and then you add 1 each time. It goes through 0, and it goes all the way to positive L. That's what they're trying to describe here. Did they say that? They said, they just said values are integers from negative L to positive L, right? Including 0. So casually written right here, including 0. But you can see here, so you go from what negative L is. In our case here, L is just 0, so that means you're right in the center. ML is 0. Here, L is 1. So if L is 1, add a negative to the number, negative 1. Add 1, you get to 0. Add 1, you get to positive 1. Is that positive 1 the same thing as positive L? Yes, then you stop. Okay? Let me go ahead and work this in sequence so you can see. When L is 2, start with negative 2, negative 2, negative 1, 0, plus 1, plus 2. So you go from negative L to positive L. When L is equal to 3, go from negative, negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. Okay. So what do all of these values code for, though? This gives you the specific shape of the orbitals. So I'm going to write here, based on these m sub L values, I can say here there's only one type of this shape, one shape. This one here, 1, 2, 3, there's 3 types. 1, 2, 3, 4, 5, there is 5 types of those shapes. This one here, 1, 2, 3, 4, 5, 6, 7, there is 7 types of the shape. Right? So when L is 0, we said that was round, right? There's only one type of round, spherical. You look at it to the left, to the right, it's still round. No difference. When L is 1, apparently there's 3 different types. When L is 2, there is 5 different types of the shape we see here. Remember L is 1 was like this? How did you get 3 different types of that? I'm going to show that to you. L is 2, it was like this. How do you get 5 different types of that? I'll show that to you. When L is 3, that was the flower, right? How do you get 7 different types of the flower? Once again, that last picture. Okay. So you see what they had here? Since I told you this was our goal. Here you can see L is 1. We only have one type of S, right? When L is 2, figure 8, look. And then this is the P shape, right? You see how they write it here? P sub negative 1. The negative 1 is for the M sub L value. Look at that, right? P sub 0. So P is the name of the shape, and the sub 0 is for the M sub L value. P sub 1. Now, different books write it differently, so don't get married to like one way and then stick. Trust me, don't make the mistakes I made. I made them all, so you don't have to make the mistakes. If you make the mistakes, just move on, okay? Different books write differently. So versus memorizing one way it's written, be fluid. I'll tell you right now, I hated being fluid. When I was first learning this, I'm like, can we all agree on like one way to write this? Okay, I'm still learning this. I haven't even figured out how to run. I'm crawling. And you all have shown me different ways, but I'm just telling you the reality. There are many different ways that scientists write this out. Okay, so yeah. So how the P is different? If you look at the axis, first of all, this axis is not messed up. This is chemistry, y'all. Chemistry tries to distinguish themselves. We are not math people. We are chemistry. You see how these axes are labeled? The top and the bottom axis in math is your y-axis, right? Now in chemistry, the in and the out axis is the one that's y. Then the left and the right one is the one that's x. Okay, everybody agrees on x. Top and bottom is now z. So here, on this one here, this is called P1 here. It's also called PY. Why? Because the figure 8 has the y-axis passing right through it. This kind of reminds me of a kebab. But you know what I'm saying? Like the meat and the skewer, the axis is acting like a skewer passing right through the orbital. Like that. And over here is the z orbital. So this is called PZ. The z orbital passing right through the figure 8. And then here, this is called the PX. So PX, PZ, PY. Right? Px because the x-axis is passing right through the orbital. With the s, there's no variation really because all the axes pass right through the orbital. So we don't call it sx or sy or sz because all 3 of them pass through the center. We just call it s. Okay? And then this one here, I would say as far as recognizing the shape, you need to go to this here, this level. You want to be aware that the F is like a flower, but it's really 8 circles, right? But F, they may refer to it in the quantum number, but at your level, you will not be asked to draw a figure 8. That's why you can see my drawing is terrible, right? You will not be asked to draw that figure 8. I mean, sorry, the flower thing. But right here, look at it. How do we get 5 different shapes? Once again, it's all about the axes, right? The orientation. Here we got 4 balloons. And in this case here, we have a plane. It said D minus 2. This is the M sub L value. Minus 1, 0, 1, 2. So here, wait, this should have been L is equal to 0, right? L is equal to 1, L is equal to 2, and then here L is equal to 3. Because you can see the highest value of L corresponds with that. Yeah, L is 0, 1, 2, 3. Corresponds with that. So here you can see the different circles, 4 circles lying on the XY plane. How do I know what plane it is? Both the X and the Y are going through the bubbles, right? Like the 4 balloons. Over here, it looks like, let's see. It's really hard to tell, but it looks like it's XZ. X and Z are passing. So the balloons are kind of vertical, up and down. So that's the X and Z plane. Here the balloons are lying on the table, right? Or on the ground. That's the X and Y plane. I'll skip over this and explain that in a little bit. Here, the balloons are in the, from where I'm looking, it looks like the Z and the Y plane. So it's like in and out, towards me and away from me. And then this one here gets very complicated because in this one here, it looks just like the first one, right? It looks so much like the first one. But I'm just going to tell you right now, even for me, this is hard to tell. But one of these is called dx squared minus y squared, while this one here is dxy, dxz, dz squared, dyz. Okay? The one you want to recognize in general, the d orbital has got 4 bubbles or 4 leaves. Okay? You want to recognize that dz squared is very different from the rest of them. dz squared looks like a p orbital with a floater. Is that what it's called? Something on its waistline. That right there. It looks like a floater on its waistline. That's called dz squared. How do I remember these letters? Based on the plane that they're on, right? It's a little hard to see this. I just try to figure out, is it lying down like on the table? Is it going from right to left? Is it going from in to out? And I use those to remember that. But you guys have your resources, so it's a lot easier for you guys, okay? And then dx squared minus y squared, that's the one where it's hard to see in these pictures where the axis is going right through the bubbles, like a shish kebab. That's when you get this orientation right here. Okay? So real quick, the periodic table, let me show that to you so y'all can see how this works out. And I'll start here when we meet on, oh no, that's the last quantum number. I'll start here again when we meet on Wednesday. So this is how it works out, my big concert hall. Okay? Here, now our M sub L is 0. So yeah, I'll start over with this one here. I'll say start here. Because I figured I want us to go over this one here twice. Start here. So M sub L is 0 for this. Remember, this one here had small circle, big circle, big circle, big circle, and it gets bigger, right? So for this one here, M sub L is 0. So now we just learned N is 1. This whole thing, L is 0, M sub L is 0. Don't forget, for this one here, L is 1, L is 2, L is 3. Depending on what column within the block, you have different M sub L values. Over here in the P block when L is 1, you have M sub L, -1. And you see how they're blocked in 2s? Because these 2 elements will be roommates. Okay, so here we have, let's see, I have my periodic table here. B, C, N, O, F, and E. Boron and carbon are roommates. They're in the same orbital. Nitrogen, oxygen, they're roommates. Now they're not in a room, so I call them orbital mates. That's not really an official term. That's the term I use. They're in the same orbital. So if you're in the same room with somebody, you're a roommate, right? Same orbital, orbital mate. Fluorine, neon, orbital mates, right? So here I'm going to write these in: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So we're going to be working on a couple of these so that we'll end here. Hydrogen and helium. Okay, just like we did before, right? We're going to provide the 3 quantum numbers and then we'll end here. So with the 3 quantum numbers, what can you say about helium based on what we know right now? So I want you guys to give me the quantum numbers in the order of N, L, M sub L, right? So in that order. So for helium, what do you think the energy level is for helium? Anybody? Okay. So for helium it's 1, right? And then what's the L value for helium? Very good. I wrote this somewhere, so you want to write L equals 0 so you can keep track of it, right? 0. Okay. What's the M sub L value for helium? So we're going through and doing these, right? Also 0. Very good. Yeah. So the electron in helium, the last electron, is an energy level 1, very close to the nucleus. It has a generic shape of a sphere, and that's the only variation we have. So yeah. Okay, we got it for helium. Done. Next one, let me highlight something here. Iron. Let's do iron. Okay. Now for iron, I guess I'll erase this right here. We'll do iron right here. What's the energy level for iron? Very good, Manuela. Yes, it's 1 less than this one here, right? It always starts at, with iron, it always starts at energy level 3, that D block right there. So 3, comma. What is the L? L is 2. I wrote it right here, right? L is 2. So you don't get confused. It's kind of, as I'm saying, if you write this out on a periodic table, it will help you very well. Very good. Okay, now we got the M sub L, which is labeled like right there, right? Yeah, 0. So you see with the M sub L, I put it like that. I don't know why, but it just worked for me. And yeah, so all the elements in that row have the same M sub L, 3, 2, 0. Yep, very good. Okay, let me pick one from here. Let's do fluorine. And then that'll be the last one. I'll let you guys go for real, for real. Okay, fluorine. Once again, starting with the N, the L, then the M sub L, and that will be the last one. Ah, very good, right? Because remember, helium was on top here, where the energy level was 1, but we moved helium over. So this one starts with energy level 2. So 2. That's the tricky part. But once you go over it at home, after this, come Wednesday, yes. Okay, so we got that. What is our L value in this section? Okay, yeah, I labeled it right here. L is 1. And the M sub L? Yeah, 1. It's labeled right there. I really strongly suggest you do one of these for yourself, right? Or print this out. I mean, well, not the one that I wrote on, but you know what I'm saying? Like, write one of these for yourself because it will help you. I am one of those tangible learner. That's not a saying. It's just something I made up. which is I have to be super involved in what I'm doing to really care enough to even learn it, right? Ergo the concert, all that crazy stuff. But once you start writing this out, then this stuff that's so abstract and unrelatable becomes relatable, right? All of a sudden you're part of it. So anyway, guys, this is all I have for today. It is cold out there, but please stay warm. If you have to go out, drive safe. I'm not seeing a lot of cars on the highway, but yeah, I'll see you guys on Wednesday. Oh, I forgot. So you say start here. Okay, start here. Okay. Yeah, see you guys Wednesday.